All right, this is functional 2, at least in the order that I've created this set of talks. We're going to look at PBE. So the philosophy on PBE is different from the other 3 we'll look at. There are no parameters to be fit from experiment. It's purely exact conditions that are used to determine this functional. Their aim was to keep the functional simple, and they want to be able to implement it simply, and that will be in comparison to their own functional, Purdue-Wang 91, which we'll see tries to satisfy more exact conditions. This functional is going to satisfy a set of known constraints, but only those that improve on LDA at the GGA level. So this is sort of an interesting thing. I think it was Jane who was asking, well, why is it that in a GGA you can just throw out things that you don't think are important? Because it makes it better. And here's another one. There are a whole bunch of exact constraints that Purdue-Wang 91 uses, but it turns out it doesn't improve the results. So they just said, for PBE, they said, well, we're not going to use those. So the people involved are John Purdue, who was at Tulane for a very long time and is now at Temple. Kieran Burke, who was a postdoc for Purdue and then went to Rutgers and is now at UC Irvine. And Matthias Ernzerhoff, and they were responsible for this function. So as I said, the roots are in Purdue-Wang 91. You can look that up. It's got a lot of constraints. It's a sort of an ugly mess analytically. And it satisfies a whole bunch of exact conditions, but from their perspective, too many, because some of them break the performance relative to LDA in some limits. They also felt the functional had more parameters than needed, so PBE is just going to keep the parts, they improve the results, simplify the functional, and no fit parameters. So there's no experimental input here. All right, so it's going to get, I'm sorry, what that T is, correlation related to gradient. Oh, no, T is related to gradient. It says that this is just another representation of essentially a gradient correction. So what do? They get the slowly varying and rapidly varying limits correct, and they get the high density limit correct. Now, I'm not suggesting that you should get any physical insight over the form of H, but what this really is look, this is the uniform electron gas contribution to correlation, and here's an augmentation, and that's what this term is. A looks like this. You know, in terms of physical form, I don't get it. But what I do know is it gets the right answers in various limits. So here's exchange. Here's what they were shooting for. They want correct scaling with uniform density scaling. That's basically taking the density and inside of it scaling R so that the density can expand or contract. And they wanted the correct behavior with that. Spin scaling is what happens when you have different amounts of alpha and beta spin. They wanted that. They wanted the linear response for small density variation. So we basically wanted to behave like LDA when the density didn't change all that much. And here's this thing called the Lieb-Oxford bound. And it says that EX, that's just the exchange part, has to be greater than or equal to EXC, which has to be greater than or equal to this number times LDA exchange. I don't understand it. I'm just going to confess. You know, I've looked at it before. It's been a while. Maybe I understood it one time. I don't understand it now, but it's a constraint they want. And here's what they come up. It's a relatively simple form for exchange. Kappa is the one parameter, but it is fit by satisfying constraints. And what this again does, it take EX, that is the uniform electron gas, exchange energy density, and you multiply it by Fx, this term here, and it gives you, once you integrate, the exchange for the GGA. Now, this plot's always befuddled me, but here's what it's basically saying. Let me tell you what RS is. RS is 1 over the density, 1/3 power of 1 over the density. So it's basically the radius of an electron. So if RS is 0, this is high density limit. If RS is infinity, this is the low density limit. This is FXC, so you see it starts at 1, so greater than 1. and it's how it modifies EX here. This C is that there is spin compensated, so there's as many alpha and beta spins as each other. And lastly, I'm sorry, the axis here got cut off, but this is S. It is the reduced gradient. So it's saying, look, here at 0, I have a uniform density. And here's what my augmentation factor would be if the density varies. And at each point, this I can go up and say, how's the change if the density varies? But this is also telling you how the augmentation changes with gradient, with the fact that the density is no longer uniform spatially. It currently is a heavily used functional for solids. I think I've said to you a few times, this is the most cited paper in the history of physics, period. It is not a hybrid, which means that it does well for periodic boundary conditions. It generally improves on the LDA, and there is a hybrid version that has been used in chemistry, and that too was not fit. It's, simple arguments based on the adiabatic connection formula that gave rise to a 25-75 hybrid. But it's not as good as others we use for chemistry. Try it, but you know, it's okay. But just to give you a sense of how it does, these are atomization energies of molecules, and you have a whole bunch of different. So I'm going to pull it apart, and I'm going to figure out what the energy difference is between the molecule and the atoms. And of course, UHF does a terrible job. There's no correlation. Local spin density does a better job, but it's not great. Purdue-Wang 91 with a lot of parameters and some overfitting does pretty well. PBE does at least as well, and it does at least as well with a simpler form and no adjustable parameters. Okay, so that's PBE.